Hi, good morning. How are you? Thank you for joining us today. My name is Paul Hutchinson. I've worked now for Jubilee for over 11 years. Before that, I did previously work in FG Wilson. I was there for 16 years. So it's a long time to be working in the power generation business. So for today, we're going to talk about the basics of synchronization. Okay, today is not designed to give you a full, in-depth knowledge of how to synchronize, but more, we're going to tell you about the things that we need for successful synchronization. Okay, if you have any questions, please use the chat function, and we will answer the questions either as we go along or at the end, which we should have time for some questions. But please bear in mind that the questions you have should be relevant to what we're talking about today, okay? A lot of the questions, I know you have lots of questions that you want to ask about synchronization, and maybe today will not fully address or answer those questions. All right, so today is about the basics. Because there are so many different types of synchronizing control systems out there. You've got lots, you've got Woodward, you have Deep Sea, you have even some of the Power Wizard, Caterpillar style. And there's lots and lots of control panels out there. So obviously we can't answer all of those questions on it. But today is designed to give you an insight into what we need to look for when synchronizing. Okay, as I say, any questions, please feel free to ask them as we go along in the chat function or at the end of the presentation. Okay, we should be here for approximately 60 minutes, give or take a few minutes. If we don't get to answer your question, I will answer your question. We'll have your email so you can submit it, and we will get back to you and try and give you an answer on it. So we will. Okay, so moving on, just gotta, we have some minor issues here. Hopefully everybody can still hear me, okay? So today's objectives, what we're going to talk about today, the introduction about what is synchronization. We have our speed and voltage control. Okay, because remember, we need speed of the engine and the alternator, and of course the voltage control on the AVR. Some basic load control modes. There are lots of different types of control out there, but we'll talk about some of the basic ones. And how the system works. What is a typical synchronizing system? Okay, so we'll go through all those topics briefly today, I say in the time space we have. Just for future reference, we do offer, this course is normally a full 2-day course that includes practical training. So you'll do a theory course 1 day, and then most of the second day would be all hands-on, wiring the gensets, programming, and all of those things, and commissioning. So there's a lot to talk about in those 2 days. So that's why in 1 hour, it's hard to cover all the topics. But we'll, as I say, we'll see how we get on. So synchronization, what is it? Well, it's the matching of one AC waveform of an electrical generator with another alternating current source, okay? For the two systems to be successful, okay, we have 5 main things that we need to meet. Now, there are more than 5, yes, I understand, but the 5 basics that we need to meet for successful synchronization, okay, are the following. So we have the voltage of the two systems. The AC voltage, whether it's 380 volts, whether it's 400 or 415 volts, we need to be able to ensure that the voltages of the two systems are exactly the same. Okay, and remember, for successful synchronization, that voltage is important, that on both or on all sets that you're synchronizing together, is very important that it is exactly the same. So, as we said, for successful synchronization, the voltage of the systems, I know this says 2, but remember we can have multiple systems, right? So the voltage of the two systems, or all of them, must be exactly the same. Okay. Again, as part of your checks, you would use a calibrated meter, normally something like a fluke meter, and you would check the output of each of the alternators and other source that you're synchronizing to ensure that the voltage is identical. Okay, so you should be reading the same voltage on all gen sets as what you're synchronizing to on your source. If you don't, it can cause a lot of problems during synchronizing or when you're trying to load share or other things. So the voltage must be exactly the same on each or every gen set that you're trying to synchronize. All right. Speed of the two systems. So your frequencies, your RPMs must be exactly the same to ensure that when you're trying to synchronize, it is much quicker when if you have the two speeds exactly the same. So whenever the control panel, the synchronizer controller, is trying to adjust the speed, it has little adjustments to do, but it will result in the whole system synchronizing much faster. Okay, so these two will help with that. Phase angles, okay, the two systems, as I said, or more, those phase angles, although the synchronizing controller takes care of that, but the two phase angles must be close or within. As you'll see when we go through here, the two of them must be very close to each other. Okay. The next one is the number of phases in each system. Normally, that would be 3-phase, 4-wire. So you have your L1, your L2, your L3, and your neutral. Okay. And of course, then the direction of rotation. So L1, L2, L3, or red, yellow, blue. Okay. They must be the same. Again, otherwise, you'll have big problems when you're trying to synchronize. Okay. So those are the 5 main basic things that you need to have, or to at least be matched. Now, I know there are more, and this is by no means exact. But these are the 5 basics that we need to have control, or they need to be near each other for successful synchronization. So as we said earlier, if you do have any questions, please put them on the chat, and we will try and address them as we move through the presentation, if it's to do with a certain slide. Okay, so please feel free. If not, we'll try and answer as many questions at the end of the presentation. So voltage match. So we said earlier, the voltages of the two systems, or all the systems, must be within a very close percentage of each other. Okay, so here we can see we have our two AC sources, our AC1, AC2. So this could be from the two different gen sets. Okay, we need to get them as close as possible to each other. And again, yes, the synchronizer will control the voltage output of the AC alternator to try and bring the two voltages to be around the same, okay? But as a pre-commissioning check, you should already have checked the actual individual output of each genset or gensets or other source to ensure that the voltage is exactly the same, okay? And I can't stress enough at how important it is that those voltages are exactly the same, okay? Being close enough is not good enough. They must be exact. Because remember, how good the system works is only as good as the person who commissioned it. So the voltage is one of those that has to be exactly the same on each set. And then the synchronizer panel only has a small adjustment to do when it's trying to synchronize, and it will synchronize much faster. This percentage here, you see, that will be set in the configuration or the programming of the deep sea controller or other control system, whatever one you're using, okay? Okay. So voltage matching, continuing on as we're talking about the voltage matching. So when a genset is in parallel, the mains, a difference in voltage before paralleling, remember we're talking here about the mains. So we're synchronizing, or we're talking, in this case, of synchronizing a genset with the mains, okay? Not genset to genset. So a small difference in the voltage of the genset will not change the voltage of the bus. And by the bus, we're talking about the actual mains itself, okay? The connection of where the other side of the breaker from there to the mains, where we're connecting. However, if there is too large a difference in the voltage, as in if it is too low, then it is possible, remember the mains or the utility is a much larger source. Okay, so if the voltage is too low, there is a chance the AC alternator could be motorized, which will then cause damage to the engine and or the alternator and other equipment. So again, going back to what we said, it is important for the voltages to be exactly correct. Okay. If the two systems of unequal voltage are paralleled, then we see lots of bad things starting to happen. Okay. We'll talk more about that as we move through the presentation. Okay. Frequency match. Okay. So the frequencies, again, must be within a small percentage of each other. As we said earlier, the frequency of the alternator, remember, it is controlled by the engine because the engine and the alternator are mechanically coupled together. So any changes in the engine speed will affect the frequency of the AC alternator. We want those to be as close to each other as possible, again, for better synchronization and less problems when we're trying to synchronize. Okay. This percentage is normally programmed. It's a physical setting that we program into the synchronizer controller. Okay. And there will be defaults already in there for synchronizing, but it's important to ensure that you get those defaults correct. Phase angle match. Remember, we talked about the phase angles of the voltages, okay, to ensure they're all starting and all in alignment. So here we see our AC1 and our AC2. Okay, it is important for those both to match or to be within a same amount of percentage or degrees, as we talk about in this case, of each other. So we have our two different sources. We want those to be starting phase angles to match in as best as possible. Okay. Again, that is controlled by the synchronizer. Okay, the panel, whatever the controller is, as we said earlier, it could be a deep sea, it could be a Woodward, it could be something else. Number of phases. We talked about this earlier. So number of phases in the system. Okay, so here we have a generator, just as an example. We have either another generator or the utility or the mains. Okay. Red to red, yellow to yellow, blue to blue. 3 phase. Okay. The neutral has been taken out just to make it easy to see and understand. Phase rotation. It is important, as we said earlier, for the phase rotation to be correct. In this case, we have our red, yellow, blue. And whatever the second system is, phase rotation should be red, yellow, and blue. The two of them have to be the same, or L1, L2, and L3. So it's an important check to make in your pre-checks before you try to synchronize, is to ensure that all of these are correct. Why is synchronization important? Well, as we know, when we bring 2 or more systems together, okay, it's important that the synchronization is correct. Okay. If it's not correct, we can see problems. Okay. It can result in mechanical stresses, okay, electrical stresses, power surges, causing major damage to one or both of the systems. All right, so this is going back to our pre-synchronization checks. Incorrect synchronization under the worst conditions could be one or all of these things. Okay. Power surges build on each other until one or all of the systems, depending on how many you have, are all disabled. Okay. High currents, placing both systems, okay, under stress. Again, bleeding down the line, if it's long enough or done incorrectly, complete damage on one or more units. Bent shafts, broken coupling discs. Okay, because remember the engine and the alternator are both connected together. All right. One system can lead to a dead short in the other, or we could see voltages being twice what they should be on the system. Again, these are just some examples of what could happen. Okay, so synchronization is one of those things that must be done correctly. And we should all have had training. As I said at the start of the presentation, we do offer customized or bespoke training for all customers and dealers. Okay, you can contact us for further information on that. So, how is synchronization accomplished? Well, normally we'll already have one system online, whether it's a generator or whether it's the mains. Okay, We always have to have a voltage there as a reference for something for the other sets to synchronize to. Okay. Again, in the old days, depending on how old you are, some of these would have happened previously years back. All right. We used to have our controllers for the speed and the frequency. You would have been watching, you had your 3 lights. I'm watching the 2 lights changing very slowly. Okay. And you'd be watching your sync meter when it hit the 12 o'clock position. And at that point, we used to hit a close breaker button. And a lot of us used to go and hope for the best at that point. So that was the old way we used to synchronize the systems together. But today, for the new systems, with the advance in technology, it's all done automatically for us, which is good. Okay, so the synchronizer controller, as I said earlier, if it's deep C, again, deep C is one of our most used panels. Depending on the settings we have and we've configured into it, it will do everything for us. Okay, from the moment of when we want to synchronize, it will take care of the speed or voltage matching, all of those things. But the one important thing that we should have done before that is individually commissioned each set. Okay, so it is important that we have commissioned each set individually. So how does it all look? How does it all fit together? Okay, the first thing, we have our synchronizer. So as we said earlier, that could be a Woodward, it could be a deep C, whatever your synchronizing controller or panel type is. All right. We have our engine, we have our alternator, we have our AVR and the AC alternator. Remember the AVR must be one of the AVRs that the controller, the synchronizing controller, can actually control. Okay, so sometimes if you want to synchronize, you need to upgrade the AVR, to change the AVR type, to ensure that the synchronizer can control the output of the AVR. And it will communicate with it in a number of different ways. Some are a voltage bias, some are CAN bus, some may even be PWM. So say the technology with all of those are advancing so fast. So depending on which system you're using, ensure you can use a bias or some communication between the synchronizer going to the AVR. The AVR will then control the voltage output of the alternator. Also, the synchronizer needs to be able to control or at least communicate to the electronic governor or ECM that controls the engine speed. Okay, so again, we have various different ways of communicating with that. Okay, that can be, again, a voltage bias signal. It can be through CAN bus, or it can be through PWM, pulse width modulation, just depending on the engine type. The other thing the synchronizer needs to have, it needs to know our bus voltage. Okay, so whatever source we're trying to synchronize to, it needs to go in here and have a voltage reference. Again, the output of the AC alternator will also be fed into the synchronizing panel. It needs to be able to see that. So it looks at the voltage here, and it looks at the voltage here to ensure that the two of them are exactly correct. Okay. Once the synchronizer is happy with our 5 things we talked about, synchronization, once it's happy at that point, we'll then send a signal to close the breaker, okay, the genset breaker. At that point then, we're in sync with the oncoming or the other source, okay? And the controller here continues to monitor that throughout the whole time. It is in sync or parallel, if you want to call it, with the other source. Okay, it's always constantly adjusting to ensure that everything stays as it should be. And it operates according to the set points or the operating mode that has been programmed into it. Okay, so frequency or speed control, because remember, speed and frequency are linked together. As we said, it's controlled by the synchronizer, and depending on the speed reference put into the synchronizer, it then looks for that speed coming from the engine and frequency of the AC alternator. So it's always adjusting to ensure speed remains constant with the source that it is synchronizing to. Okay. If your engine has a mechanical fuel injection pump, okay, you can't synchronize with a mechanical fuel injection pump. If the engine manufacturer have an electronic governor that can be upfitted, then we need to fit that. Okay, because remember, speed needs to be able to be adjusted by the synchronizer panel. Okay, and if it's a mechanical fuel injection pump, well, this can't be done easily. Okay. So as we said, synchronizing, it's a word we use. It covers 3 main fundamentals. Okay. So 3 main fundamentals prior to paralleling or synchronizing our supplies together. Okay. The first one of those is frequency matching. Okay. So frequency, as we said, is related to speed. Okay. So we're talking about the engine speed. It will change so that the two sources get to be within an acceptable percentage of each other. All right. So we see them here, one source frequency and the second source frequency. Okay. The next one is phase matching. Okay. So we know in this example that we see here, okay, our voltage is the same because we can see our peaks. And our troughs are the same. Okay. But they're not in phase with each other. We want these two to be much closer together, okay, or within an acceptable limit. Okay. How do we do that? The electronic governor controls that. It either speeds up or slows down to pull the two sources to ensure that they both come into sync together. Okay. So as the synchronizer starts to adjust the speed, so the phases, as I said, come into sync with each other, you'll see them starting to move closer to each other. Okay? Gets to the point of where they're nearly or within an acceptable tolerance. Again, depending on the configuration settings that have been programmed into the control. Okay, so that's the phase matching done. Okay. So as I said as well, our voltage control. And that is controlled by the AVR. Okay, but remember, our synchronizing panel here talks or gives the AVR commands. It then raises the alternator voltage or lowers it to ensure that it matches the other source that we're coming to. So again, voltage matching. It's looking to ensure our voltages are the same. So they have to be the same height. And in this example, we can see that they're not. So I said, Deep C is one of the common controllers that we use. When we go into the synchronizing screen and we're trying to synchronize two sources, we can see our frequency difference, our voltage difference, okay? You can see just here, this small cursor. And when you're in the synchronizing screen, you will see it moving in this direction, okay? And you'll see it starting to go slower, until it gets to the point of being in the middle of here, okay? Once it's in there for a period of time or dwell time, okay? At that point, the controller is happy that it's in sync. And at which point, it will issue a breaker close command, okay? And at that time, once the breaker has closed, we'll start to see information here and here. So once it's in sync, then it will start to ramp up with the load that's on the system. Again, depending on where or how the configuration settings tell it to go to. And of course, depend on the size of genset that it is. So say each synchronizer panel will have a different screen. But as I say, this is the Deep C one that we use. Load sharing. Again, all sets, genset or gensets online, if they've been configured correctly, they will all load share according to their size, okay? Proportionally to their size, okay? Remember, active power is our kilowatts. And kilowatts is generally put in with resistive. Reactive power, VAR, is what we use to supply likes of capacitive and inductive type loads and others, okay? And you'll have a mix, obviously, of each of these. So the control mode that we set in the Deep C controller, okay? So if we're in active power, even though the two systems are linked or synchronized together, okay, at the same frequency, once that breaker closes, the frequency for all purposes and intentions will be 50 Hertz. How does the genset take on load? Well, it increases the fuel. So as it increases the fuel, it takes the load on, even though the frequency stays constant at 1500 RPM. So by increasing the fuel, it will take on more load. And then obviously, by decreasing the fuel into the engine, the load will get less. Reactive power control. Okay, so increasing the DC voltage to the alternator field winding. Okay, so we're talking about the AVR bias. Okay, keeps the output the same, but will increase the genset supply of VAR. Okay, voltage amps, reactive. Likewise, going the opposite direction. Okay, it will keep the voltage the same, but it will decrease the genset supply of VAR, voltage amps, reactive. Okay. As an example, here we have a typical system. Okay, so we've already looked, so what we've covered so far is we've talked about the 5 things that we need for successful synchronization. Okay, we've talked about each of the different types. So we've talked about speed control, our voltage control. We've talked about our phase rotation, number of phases, all of those things. Okay. By that stage, we've all individually commissioned each genset to ensure our voltages, our frequencies, everything is good to go. Okay, so a typical system, in this example, I've only got 4 gensets. With the deep sea controller, you can have up to 32 gensets synchronizing together. Okay, each genset and controller will have its own network address and network priority. So a network address, this could be simply number 1, number 2, number 3, and 4. The priority, so what we mean by that priority is whichever one we want to always run in a load-dependent system, okay? Depending on how it's set up. Okay, so you could have this has a priority of 1. This could be 2, 3, and 4. Okay, so each one will always have a priority. So whenever they're load sharing and our load levels are going up or down, okay, it'll be switched on or sequenced off in reverse order. Okay, so that's when the priorities come into play. The other thing we can do is we can program to ensure that all the sets are within a margin or a window of each other on the engine hours run, so that we don't have one genset sitting maybe at 10,000 hours run and another genset sitting maybe at 300 hours run. Okay, so you can set in a balance, and the system will automatically take care of that. Again, I am referring to the deep sea control system. So here we see we have our load. We have our genset fitted, in this case, with an 8610 controller. All right. What happens, although we don't have it here, but in this case, they receive a signal because the mains has failed. At that point, the ATS will send a signal, which again is not shown here. I've just taken it out, but it will send a signal to the deep sea controller. Okay, because the deep sea controllers, they all talk to each other through their MSD communications, so multi-set communications. They all say, okay, we all need to start up. What happens? They all start up and they'll run together. Okay, now whichever one is up to rated speed and voltage first will close its breaker. Okay, and in this case, is this one here. Okay, so it closes its breaker. And the whole idea of this system, because they're talking to each other, it has a token or a key system that it uses. So whichever one is up to rated speed and voltage, he tells the rest, okay, I'm closing my breaker. So he closes his breaker, as we see here, okay? Once that breaker is closed, that means this bus is live. Okay, and as I say, we will have other breakers fitted downstream, obviously to stop one trying to feed onto the load. As I told you earlier, we have omitted it out. So all the other sets now have a voltage, frequency, phase angle, all of those things to start synchronizing and adjusting to. So each one in turn will take the key. So once, in this case, number 1 has closed its breaker, he passes the token to the next genset, not necessarily the next one that's in line or in order. So remember, it's up to rated speed and voltage, and then it will try and synchronize. Once that is happy, it will close its breaker. Whichever one is next, in this case, number 4, he closes his breaker, and then number 3 closes his breaker. Okay, and at this point, the system is now supplying the building load. As we said earlier, depending on where the load levels are and how we've configured our network priorities, gensets will be synchronized on and offline according to the programming set points that we have programmed inside the controller to ensure that we have plenty of capacity left in the system if we start to take units off, or enough capacity to bring systems on, or sorry, other gensets online quickly to ensure as load levels start to rise. Okay, so that's how that system works. Then after it has finished, or say in this case the mains comes back, or the utility, once it's back and stable, it will take the load. Then the gensets would all shut down and then await the next signal from the mains or the utility to restart again. Okay, so hopefully that has given a bit of insight into synchronizing systems. What is required? What do we need? The basics and everything else. Just remember that each genset needs to be able to control its own breaker. Okay, so it needs to be a motorized circuit breaker of some description. Okay, ACB, any of those. Right, so it has to be capable of controlling its own breaker. All right. So we have a couple of minutes for some questions. As I say, if you have submitted a question and we don't get to answer it, then we should have your email. We can answer your question by email. Okay, but just remember the question should be relevant to what we've talked about today. Okay, so I have another computer here just so I can see what the questions are. Okay, let's see. So our phase shift and direction of rotation. If I'm understanding your question correctly, phase direction and the phase shifting should more or less be in. So you'll have your phase direction or direction of rotation, your L1, L2, L3. Okay, so they should all be going the same way. If that answers your question, I hope. What if the voltage of one of the generators is too high? Again, we're going back. We don't want to see our voltages going too high. Okay, so think back to what we said in the presentation. We can cause damage to the alternator if we're going alternator to alternator, or we're going alternator to the mains. Okay, depending on what way we're going. But we can cause damage to equipment down the line that is on the bus side or things like that. So we always want our voltages to be exactly the same. So Michael, hopefully that answers your question. Yes, Benjamin, you've asked, do the voltage regulators of all generators, should they be the same? The answer is yes, they should all be the same. Remember, that would be part of your pre-commissioning of the gen sets. Okay, so we said you get a multimeter, normally a fluke, and you ensure that what you measure at each of the breakers is exactly the same. Okay, and that you don't have a large difference in the voltage output. So thank you for that. Okay, Abdul, you have one about active and reactive power control. Again, that is designed to be outside the scope of what we're talking about today, because today is only to talk about the basics of synchronization. So what is the cause of negative reactive power in generators during synchronization? Benjamin, again, that is outside the scope of what we're talking about today. But as I say, email me, guys, and we can have a chat. But again, that would be down to the synchronization setup. Okay. If you go back to what we've talked about today, then you should be able to answer your own questions. All right. Because it's all to do with the commissioning and the setup of the genset system. Okay, as I said at the start, remembering that the system will only work as well as how it has been commissioned. Okay, so it is to do with the setup of the system. So go back to what I said, your voltages, your frequencies, maybe you have a drip CT fitted in the AC alternator, all of those things. You have to ensure that they're all set up correctly. Mohammed, loss of excitation, again, is outside the scope, but please give me an email and we'll talk about that offline. Is it a must all sets start at one time? The answer, they should, depending on how your system is working, whether you're in standby or you're in a prime application. But in a standby, once the mains has failed, the start signal should be sent to one genset, which should be talking to all the other sets, depending on how many you have. And then they should all start together, yes. Or within a short space, half a second, second of each other. Tarek, that is down to matching. Yours is on synchronizing systems suitable for building sites and stuff like that. The answer is yes. If they're set up correctly, it can be done. Again, Mohammed, questions like that, you need to keep offline. All right. Yes, you can synchronize different ratings of gensets. But one, they should all have the same synchronizer controller, and they will all load share proportionally according to their size. So yes, you can. Carlos, yes, we can synchronize power systems and PV, but again, we need other equipment to help us do that. But the answer is yes, because most of the inverters should be able to do that. They will handle part of the synchronization going from the solar side onto the AC side. Is it possible to synchronize 100 kVA to 50 kVAs? The answer is yes, as long as you remember what we've talked about today. But what you also have to consider is the actual costings of the synchronizing equipment, the motorized breakers, and all the other additional equipment. Sometimes, from a cost perspective, it's not worth it. Okay, we've run slightly over. I know we had some downtime in the middle, but it's now 5 past. So for today, any of your questions, we will answer. But if you have anything further, please contact us. Thank you for today and your patience during the small interruption we had at the start. But any questions I say, send them to us. So have a good day, stay safe, and thank you.